Good morning or good afternoon. And for some of our international attendees, good evening. I'm so excited for our presentation today. I'm excited to bring experts on geologic hydrogen to you. I know that we're waiting for a number of participants to be logging in. You're all trickling in right now. So I'm going to give everybody a few more minutes to come on in. And once our numbers stabilize, we're going to go ahead and start our presentations today. It looks like our numbers have stabilized. So I'm going to go ahead and formally start us off. My name is Roxana Beck-Mohammed. I'm the founder and executive director of the United States Hydrogen Alliance. The United States Hydrogen Alliance is a business trade association focused on hydrogen advocacy across all 50 states. We work offensively on the state side and defensively on the federal. And we're so excited to bring this important topic to you. I've worked in hydrogen for the last 16 years and have studied hydrogen in all of its forms, but this has been quite exciting for us. And I really do think that geologic hydrogen can be a significant game changer that could change the economics of the entire hydrogen industry. So it's my absolute pleasure to bring three experts on this topic to our audience here. I also wanted to give a quick reminder to you all that the United States Hydrogen Alliance actually does have a Hydrogen Policy Institute, and we published last year our Geologic Hydrogen overview document, which we just recently updated. I'll be putting that link into the chat, but also including it in the email correspondence that you'll receive at the end of the webinar. You most likely will get that email tomorrow with a YouTube link, the attachments to the copies of the presentation, as well as Yusha's updated publication. And at this point, it is my great pleasure to introduce Dr. Ellis as he describes how the USGS has approached geologic hydrogen. So, Dr. Ellis.
Thank you, Roxana, and thank you all for tuning in today. Um, so before we dive into the hydrogen story, I want to set a little bit more context for why we all are interested in this. And so this first figure shows us a graph of historic energy supply for the globe over the last 200 years, the span of the Industrial Revolution. And what you noticed, a few key things is that of course, demand for energy has increased consistently throughout that time period. And every time that we have discovered a new source of energy, it's simply added to the old supply that we've had, and we just keep producing more and more energy. But now we're at the situation where we need to replace actually all of the fossil fuels, the coal, oil, and natural gas, with renewables. And at the same time, going forward, we can expect that the demand is going to continue to rise. So there's a big challenge here in trying to actually make this transition to a low carbon future. If we look at a map here showing the potential for renewable resources across the US, you notice that we have an abundant supply of renewable energy. And so it's really not a question of do we have enough renewables? There's clearly a lot of renewables that are available, but there are many, many challenges associated with getting it at scale and getting it where we need it, and making this transition. And this is not a comprehensive list, but some of the major challenges that we face with the energy transition. And I want to focus just on this last one here that's most relevant for our conversation today. And that's about this hard to abate emissions. Most of these renewable sources are really good at making electricity, but there are other parts of our economy that rely on other forms of energy. And so these are often referred to as hard to abate sectors. And by some accounting, this is as much as 40% of our greenhouse gas emissions come from things like aviation and shipping and steel and cement manufacturing. And it's almost certain that this is going to require hydrogen, probably a lot of hydrogen, to be able to decarbonize all of these sectors. So where are we getting hydrogen then today? Well, most of it, almost all of it today comes from fossil fuel sources. We make today about 100 million metric tons of carbon per year, of hydrogen per year. And for every kilogram of hydrogen that we make, we vent about 10 kilograms of CO2 to the atmosphere. And so going forward, we're going to need a lot more low carbon hydrogen. By some estimates, maybe as much as 400 million metric tons per year. And it's thought that it's going to come from a mix of so-called blue and green hydrogen. Blue hydrogen being hydrogen made from fossil fuels, but coupled with carbon storage underground. And green hydrogen is hydrogen that's made by splitting water using renewable sources of electricity. But getting these two sources of hydrogen at scale is going to be a major challenge. We're really not anywhere close to that today. And in fact, right now, the technologies that we have are proving to be very expensive and quite mineral intensive. And so it's not really clear how we're going to be able to get to where we need to be with all this low carbon hydrogen. But what about the occurrence of natural hydrogen on Earth? In fact, there are dozens of natural processes that are continuously generating hydrogen on Earth. This is a list of some of the major ones. There are many abiotic processes that involve water rock reactions that can generate hydrogen, as well as biological processes that also generate hydrogen, and anthropogenic things like corrosion of steel. If we look at the geologic settings where we find hydrogen and look at the median concentrations, what you notice is the settings that have the highest concentration of hydrogen tend to be what we call hard rock settings, crystalline rocks and volcanic magmatic settings. But if we look over here to the far right on this histogram, you'll notice that the lowest concentrations are here associated with natural gas. And in fact, we've drilled hundreds of millions of oil and gas wells all over the world, and it's very rare to find very much hydrogen. We typically don't find even 1% hydrogen associated with natural gas. And so, for that reason, geoscientists have assumed that even though hydrogen is quite ubiquitous in the subsurface, you just don't get accumulations like you do with natural gas. And the rationale has been that it's a small molecule, it's quite diffusive, and it's very reactive. There are many biological and abiotic processes that can consume hydrogen. And so, even though it's out there, it's down there in the subsurface, we just don't get large accumulations of it. But with a little bit of scrutiny, we start to see that rationale actually starts to fall apart. And so the first thing to note is that the places where hydrogen is most likely to be generated, these volcanic, magmatic, and hydrothermal systems, these are not the places where oil and gas exploration is going on. Oil and gas is almost exclusively looked for in sedimentary basins. Additionally, petroleum exploration is not targeting hydrogen. They often don't measure for it, or if they measure it, they don't note it. They're not interested in it, and so they're not developing techniques that really would be looking for it. And more importantly, the process of generating petroleum from organic rich rocks is actually hydrogen limited. When we measure the quality of a petroleum source rock, we measure something called the hydrogen index, the amount of organic hydrogen in that rock. And what that means is if you had a deep source of hydrogen, say a deep fault where hydrogen was migrating towards the surface, and it encountered an organic rich rock that was producing hydrocarbons, that hydrogen most likely would get incorporated into hydrocarbons. So we really shouldn't expect to find any molecular hydrogen associated with hydrocarbon fluids. Now, these hard rock settings are places where mining companies are very actively exploring for mineral resources. But again, they're not looking for hydrogen. They're looking for minerals, and they are concerned about the presence of explosive gases. And they have instruments that measure explosive gases, and they quite frequently do encounter them. But those instruments don't tell them whether it's methane or propane or hydrogen, and so they simply don't know what's in those settings. So the bottom line here really is that we simply haven't been looking for hydrogen in the right places with the right tools. So another really important piece of this story is a site in Mali in West Africa, where back in the 1980s, they were drilling for water and they accidentally encountered some explosive gases. And so they managed to plug and abandon that well. And it was some 25 years later in 2012 when an oil and gas company came back and drilled a gas well with the expectation of producing methane-rich natural gas. But when they measured the composition, they discovered it was almost pure hydrogen gas. And so they followed that up with an exploration campaign, and they've identified multiple stacked reservoirs charged with almost pure hydrogen gas. And that discovery well is actually still on production, been producing hydrogen for more than a decade, and it's used to produce electricity for a local village. However, it's important to note that this is not really truly a commercial scale production. It's just a very small village and a small amount of hydrogen needed for that. But that's simply because there's not a sufficient offtake to actually commercialize this development. So when I first became aware of this and got interested in this subject, I was still concerned about what could really be the scale of this. Could this really be enough that could constitute a natural resource? And so I got together with my USGS colleague Sarah Gelman, and we put together a simple model to try and estimate how much hydrogen might be held up in the Earth's crust. And you can see the results here on the lower right in this histogram. And the first thing to note is that there's a large amount of uncertainty. This is in million metric tons of hydrogen, and it's anywhere from maybe just thousands of megatons to as much as potentially billions of megatons in the subsurface, with the median value on the order of around 5 million metric tons. But it's important to understand that this is for the entire Earth's crust. And so most of this is going to be inaccessible. It's simply going to be far too deep or offshore or in accumulations that are much too small that it could never economically be recovered. But if we think about it, just a fraction of that could be a resource. If you have 2% of 5 million megatons, that's 100,000 megatons, which could actually supply all of that 400 megatons per year that we think we're going to need for hundreds of years. And so to me, the takeaway was that there's clearly a lot of hydrogen in the subsurface, and it's just a question of is it in accumulations that we could actually find and produce economically. And I want to take a second here and talk a little bit about this notion of producing hydrogen from the subsurface, because there's a few concepts that have been put out as to how we might do this. And so the first is what we've just been talking about, natural accumulations of hydrogen. You have a deep source, hydrogen's generated potentially through a water rock reaction, it migrates through porous rocks and gets into an accumulation that has a competent seal on top of that, and then we can drill down and produce it. But it's also been suggested that because some of these generation processes are very, very rapid, they occur in real time, we can observe hydrogen being generated, that we might be able to actually drill down into the rocks, either right where it's being generated or along a migration pathway and produce it in real time, more like a geothermal resource. And then thirdly, it's also thought that we might be able to actually engineer systems to actually drive this reaction to move forward. We could drill down and inject water into rocks and get it to actually produce hydrogen again in real time. So a few things to note about this, the production from natural accumulations, this is a proven technology. We have an example in Mali where it's happening today. This is directly analogous to natural gas production and other gases that we produce. So we know we can do that. The production of hydrogen fluxes is very much in question. And in fact, some recent research has suggested that this may not actually work out. But the stimulated hydrogen is looking very, very interesting. We have a lot of research going on in this area and actually some pilot projects that are just getting off the ground right now. And so those, if we could actually get hydrogen out of the stimulation, that would add even more. That global model prediction that I just showed you was only for the accumulation. So if we could actually get any of this other hydrogen, that would actually add even more resource potential. So the next step for us in the USGS was try to identify where are the places where we should be looking for geologic hydrogen. And so to do that, we've developed a model, a geologic model that we call the hydrogen system model, where we have geologic factors that need to come together. You need source rocks, you need reservoir rocks, you need traps and seals. And then we developed a set of proxy data sets that we use then to map out where these components might be, and then we can run some statistical analysis on what the probability of their distributions. And so here are some of the maps that we've come up with where we have chances for sources and reservoirs and seals, and we can combine them all into an integrated product where we can now identify where are the places where we think it's most likely that hydrogen might be in the subsurface. If you want to learn more about this, you can go to our website. We have an interactive map where this is available, as well as the report on how all this work was done. And of course, This is not restricted to the US. This is a global commodity, and there's a lot of activity now going around, exploration activity now going on all over the globe, on every continent. The countries highlighted here in orange are where we have active exploration, where they're actually drilling wells. We have steel in the ground, people looking for geologic hydrogen. In the countries in green are places where we have data collection going on. They're collecting seismic or gravity, magnetic, other or geochemical data, trying to find the hydrogen. And then, of course, Mali is the one country where we actually have production today. And this is not just one or two companies. There are actually dozens of companies now that have started up, commercial companies that are working actively to try and find geologic hydrogen resources. But I want to really stress that this is a very, very nascent industry, a nascent field. And so there's still a lot more work that we need to do on all levels. We need to better understand what all of these components that go into the hydrogen system, as well as developing better, improved exploration techniques to find geologic hydrogen. And I think we'll hear more about that from my colleagues just now. And then also there's a lot of opportunities for building models and applying AI to how we can better understand all this. Although there's a lot of overlap with natural gas production, there still are some unique features about hydrogen that will require us to improve our engineering approaches to how we can produce it. And it's really a multidisciplinary, integrated problem that we need to bring in a diverse set of fields that can be applied to this problem. But the good news here is that we have much of the expertise that we need. It's already available on the ground in the oil and gas industry, in the geothermal world, in the mining sectors. And so it's just a matter of bringing the right people together and adopting and adapting the technologies that are out there already to put together an optimized system for exploration for geologic hydrogen. So there are a couple of last points that I want to just touch on before I turn it over to someone else here. And that is that I think there are a number of key challenges that we still face. And one of the big ones right now that I see out there is that we're kind of in a situation where there's a chicken and egg problem, where exploration companies are having a difficult time getting investors to support them without clear offtake opportunities. But yet the offtakers are saying, well, we're not willing to commit to you until we know what the resource is there. And so we have to find a way to work around this problem. The other thing that's happening right now is that there's a lot of interest in this. There are a lot of groups that are getting involved, but they're kind of fragmented. And so I think there's potentially a lot of overlap, a lot of duplication of effort, and not enough sharing of data. Much of the really important data is being generated by startup companies that it's being held proprietary for their own interest, which is understandable, but it's causing a hurdle that we need to get over. And then there's also a lot of regulatory uncertainty. This is such a new commodity that a lot of jurisdictions simply have no regulations in place, and so they don't know how to handle this. And so we need to really work on improving that. The other thing that I want to really point out also is that I don't see this as competition for other forms of hydrogen. And in fact, this is really complementary. I think the geographic distribution of where geologic hydrogen is likely to be is not going to perfectly align where the renewables are that could produce green hydrogen, or where we have existing oil and gas. And so it really can help fill in a lot of gaps where it's needed. And another point that I like to stress is that I've heard many people say to me, well, you might find some accumulations, but it's probably not going to be that big. And maybe it's only going to be enough hydrogen to run my fertilizer plant for a few years. And so I can't build a whole fertilizer plant unless I have a supply for 20 or 30 years. And so this is not going to work for me. But we have to recognize that if we find a natural accumulation of geologic hydrogen, we've now found an underground hydrogen storage site that has already been proven. And once you drill those well, you have the infrastructure for underground hydrogen storage. And so you could build your green hydrogen facility nearby and then have storage for hydrogen right there. Another key consideration is that it's most likely that any new hydrogen discoveries are not going to be of the kind of purity that we found in Mali. And so there will almost certainly be associated gases, and some of them can be valuable resources like helium, but at the same time, there could be other ones that could be difficult to mitigate, things like hydrogen sulfide or potentially CO2. So I'll just leave you with a few links for some other information, some interesting other videos that are available if you want to learn more about this. And here's my contact information, and happy to follow up with anyone. So with that, I'll turn it back to you, Roxana.
And thank you so much, Dr. Ellis, for making this so simple. But this was really helpful, and thank you for addressing this chicken and egg situation. It's been the plague of the industry in general. We've had too many chickens and too many eggs, but I've been trying to explain to everyone that it's a multidimensional problem, and that's exactly what we're addressing in our conference May 28th in Detroit, Michigan. We're going to be talking about geologic hydrogen. We're going to talk about cross-border collaboration with Canada. We're going to talk about offtake, but essentially it is in our greatest interest for us to make sure that we can create enough real stability across the marketplace. And with that in mind, I want to actually bring Dr. Zhang up, and we've been really lucky that Dr. Zhang and Dr. Lee has been able to present actually at one of our conferences before and address a lot of important questions by policymakers. And we look forward to hearing more from Dr. Zhang at the moment.
Thanks. I'm sharing my screen. Yeah. Can you see my screen?
Yes, thank you.
Okay. Hello, everyone. My name is Mengli Zhang. I'm a research assistant professor at Clark School of Mines. It is my honor to be part of this webinar and to present on geological hydrogen as a primary energy resource. For decades, we have known that no single energy source can meet humanity's needs. A secure and sustainable future will require a combination of resources: wind, solar, geothermal, and hydrogen. Traditionally, when people mentioned hydrogen, they were referring green hydrogen produced with wind and solar. These resources seem unlimited, but the challenge lies in the supply chain. Building solar panels and wind turbines requires vast quantities of metals like copper, making mineral availability central to energy security. To put this in perspective, imagine all the copper mined since the Industry Revolution, the wiring in every home, office, and city. Now double it. That's how much copper we need to be mined in the next 20 years just to meet the clean energy demand. So this looming mineral shortage could slow the energy supply and raise national security concerns. This is why geological hydrogen is so promising. The United States holds vast untapped potential for this resource, which could serve as a primary domestic energy supply. According to the USGS estimates, as Dr. Ellis just mentioned, the total potential energy from geological hydrogen could power human society for centuries. Then the critical questions are, where can it be found, and how do we do so in an environmentally responsible way? The answer begins with geophysics. Just as radiologists use MRIs or CT scans to see inside the human body, geophysicists use airborne and ground sensors to scan beneath the Earth's subsurface. At the Clark School Mines, I apply those similar skills to find clean energy resources. To understand how our team detect hydrogen, we first need to know how it forms. The process is called serpentinization. When iron-rich rocks react with water, they transform into new minerals and release hydrogen gas. This reaction is invisible to our naked eyes, but geophysicists can detect its signatures using magnetic, electrical, gravity, and seismic data. Often, our search begins at the surface. One of the most intriguing indicators is the appearance of fairy circles, subcircular depressions seen in places like Nebraska and North Carolina. This led us to ask, is hydrogen being generated directly beneath these circles? To find out, our research group invested subsurface structures and fairy circles in Nebraska. Using electrical surveys we collected in 2024, we developed subsurface resistivity model. These models revealed that hydrogen is seeping through the rims of fairy circles rather than their centers. A finding confirmed by soil gas samples showing higher hydrogen concentrations around the edges. So, should we drill at the center or rim of a fairy circle? The answer is neither. Actually, these circles are leakage points, not accumulation zones. The real hydrogen reservoirs lie deeper and often offset from the visible surface features. To locate them, we scale up our investigations to areas spanning hundreds of kilometers, characterizing the broader source rocks that generate and trap hydrogen nearby. Therefore, in contrast with the reservoir-centered strategy in oil and gas exploration, we propose source rock-centered strategy in geological hydrogen exploration. When we say source rock, it may sound abstract, but interesting geological hydrogen source rocks are more familiar to us than we realize. I like to check local museums when I visit a city. When I checked in a museum in Iowa City, I was pleasantly surprised to find a seated woman statue made of serpentine stone, a rock closely associated with hydrogen generation. In fact, the geochemical process responsible for geological hydrogen production is called serpentinization, named directly after this type of rock. Because there is a lot of such source rocks beneath Iowa, the state clearly has significant geological hydrogen potential. Meanwhile, Iowa Geological Survey has preserved a large collection of core samples, providing valuable materials for revisiting and advancing geological hydrogen research today. You can see how many core sample boxes in their facilities. It is no doubt that Iowa has been the hot area to explore geologic hydrogen. At the Iowa Geological Survey, our team examined and sampled archived geocores, which provide valuable ground truths for interpreting geological data. These cores give us direct evidence of rock types capable of generating hydrogen. Here is a photo of an old well in Iowa and its relative locations in the range of Mid-Continent Rift. The depth of the well was down to 2,000 feet, and hydrogen presence was documented. In Iowa, hydrogen presence in multiple boreholes, and this information was documented in publications and logging records as early as 50 years ago. Now the challenge is how to find the geologic hydrogen subsurface. The solution could be geophysics. For example, magnetic survey are conducted by aircraft carrying sensors to measure the response to underground magnetite content, which can reveal rock types and hydrogen potential. Gravity surveys commonly conducted on the ground surface, but it can also be done in the air, detect anomalies such as those related to the Mid-Continent Rift. It's a promising hydrogen target, including Michigan, Minnesota, Wisconsin, Iowa, Kansas, Nebraska, and Oklahoma. Geophysics enables us to scan and image the rocks in the ground over a large area so we can understand the geologic hydrogen systems and then zoom in on where to drill. We have a Spotify podcast about geologic hydrogen explorations. More details, you can check this podcast. As you look at these remarkable fairy circles, remember they are windows into a hidden energy resource. Natural hydrogen is being generated beneath our feet today. With geophysics, we can pinpoint where it forms, recommend drilling coordinates, and estimate accumulations. This is not just a science. It is an opportunity for the United States to secure a sustainable domestic and long-term energy supply. Thank you so much for listening to my talk.
Thank you so much, Dr. Zhang. That was so great. I love that so much. I please actually, if you don't mind, share in the chat a link to your podcast, and we'll make sure to put that in our email communication going out tomorrow. So thank you so much. That's so exciting. Dr. Lee, please, the stage is yours. Oh, Dr. Lee, you're still on mute. Oh, Dr. Lee, you're still on mute.
Mute. Can you hear me now?
Yes, perfect.
Oh,
Thank you.
excellent. Okay, great. Well, thank you for the two previous speakers for setting the stage. And so I'm going to talk about, my name is Geoffrey, also work at Geological Mines. And I'm going to talk about geologic hydrogen potential in the US states along the Mid-Continent Rift. So this work is done in collaboration with Dr. Mengli Zhang, and she, in fact, leads the geologic hydrogen research at Geological Mines and covers both natural geologic hydrogen as well as stimulated hydrogen, which is funded by a grant from ARPA-E. And what I am going to present is actually focusing on the imaging of geologic hydrogen systems using geophysics. And I should mention that in 2022, as early as back then, Dr. Zhang actually proposed this notion of source rock centered strategy. She touched on that earlier briefly about contrast with the hydrocarbon approach that is reservoir based. So that actually has driven a lot of our research. And also, I should comment that there's a lot of global study and a wonderful work done by Dr. Ellis and GS teams. And then also there's a lot of work in the geochemical realm. But then we think that the understanding of the geologic hydrogen system itself, it will take time to develop. So in the meanwhile, what we are looking at is based on what we can see in the through the geophysics in the underground is a phenomenological based understanding of geologic hydrogen system. So that's kind of the backdrop of the presentation I'm going to make here. And let me see how okay. So Dr. Zhang mentioned about the Mid-Continent Rift region. In US, in fact, from the coast to coast, there are a lot of regions with huge amount of potential. I think that was also covered in Dr. Ellis's presentation. But this is area the whole regions where we're focused on. In addition, we also have the focus area in regions such as UAE, ophiolite belt in there. But we're going to focus on the U.S. Mid-Continent Rift region. This is an ancient failed rift that opened about 1.1 billion years ago. So it's then stopped, but during the process, huge amount of volcanic activities deposited a lot of the igneous rocks, iron rich, that forms the really kind of right type of the geologic hydrogen source rocks. And this whole zone, actually, as Roxana mentioned, the covers from Michigan and Minnesota, Wisconsin, all the way down to Kansas. In fact, a lot of exploration activity is already going on in Kansas, part of Nebraska, and Iowa. So this is a really interesting area. And also, what happens is USGS actually has a lot of data in this area and allows entire US allows us to use public domain data to study this. So this image is the isostatic gravity anomaly in the lower 48 states of US. What you see is this continuous high gravity anomaly. That is expression of the igneous rocks placed in the Mid-Continent Rift system, pretty much 1.1 billion years ago. And of course, ever since then, there's a lot of things going on. That's really what's the interesting part that we're looking at. So if you think about the Mid-Continent Rift, you think about all these states, and visually what you see is endless farmland. Okay. And yet below there, and that is actually really interesting things happening. The reason we know that has been a lot of geological and geophysical study to understand the structure, geology, just pure research, and also for the exploration, understanding of the mineral deposits such as nickels. And so this is a kind of really cool area. So what happens, you look below them, there's stuff happening, hidden treasures, as we call it. So in particular, what we're looking at is the volcanic rocks, iron rich, and also there's right type of the hydrothermal or even the meteor water that coming down. So that actually has all the right conditions that allows the synchronization reaction to happen. So we're literally looking at the kitchen that actually cooks and has potential to produce the hydrogen. And so in general, then, how do we know this? And what we can go and use to look for this? That's where the geophysics comes in. And Dr. Zhang already laid the framework in the previous presentation. So in this case, you put this all together. We have the cover in this entire region. Below there's rift system with lots of source rocks. Above that, what we have is geophysics data. Could be from the surface, ground surface, from the air. That's what actually will give us the information we need. So, and let's look at it in details. So on the top right is index map showing that where Iowa is in the United States. And the main image which shows outline of Iowa, we're taking the chunk of the data, gravity. And what you see is this IQ-shaped anomaly, magnetic. We've got interesting features. We're going to focus on that. And then, so this is putting two complementary data sets together. On the left is the isostatic gravity anomaly. I showed part of the entire map in US I showed earlier. This one, what you see is this really strong continuous gravity high. That is literally the expression of the igneous rocks. And then corresponding to that region, you see this arc-shaped, the magnetic anomaly. It's less continuous, but way more features in it. And so what I want to is draw your attention to this slight low of the gravity anomaly and almost entirely depleted or kind of remove the magnetic anomaly in this region. So that is actually the combination of the signature of the potential geologic hydrogen system. So the reason we see that is once you have the supernazzation happening or subsequent alteration, that's commonly present in the mineral systems. There are three things happening. Supernazzation is volume expansion. It will actually reduce the density by about 30%. So you see this slight depression of the gravity anomaly. That's one clue. And then what happens is the supernazzation initially increases magnetite. Eventually, other alteration will continue or could continue. It actually has potential to deplete the magnetite. Then you end up with a signature of spent rock. That's literally what we're looking at. So that brings up the concept that our team developed is we are looking at partially supernized rock, neither fresh nor spent, the stuff that actually that supernization is going on. So this is magnetic. Other part we all know when you have the alteration happening, then you break up rock and introduce conductive phases, then you tend to have reduced electric resistivity. And this is published literature by Dr. Bedrudan from USGS many years ago that actually interestingly shows in this magnetic depression, you have in the shallow region up to 6 kilometers reduce the electric resistivity. All the evidence put together shows that you have all the puzzles together, indicating this zone's magnetic depression is actually a spent rock zone. So one of the understanding that our team put together is that you look at that magnetic depression, we think what's happening is the alteration, initially supernization happens in the center, and then it progresses outwards. So in the middle, the magnetite is gone. So that's actually you do supernization, then you have subsequent alteration. Then on the rim, that's where the supernization, partially supernized rocks is there. Then beyond that region, you have more fresh rock. So that's what gives us the clear idea where to go look for this. So we actually literally zooming in from continental prospectivity map that USGS developed, then look at the region, see where the system is occurring, then going into more like prospect detail where actually we could actually zoom in, find, let's say, 100 or 50 kilometers on the site where to do detailed exploration. So that's actually what we're our standing right now. Based on what I just presented earlier, our team put together this natural hydrogen system diagram or concept in the Mid-Continent Rift. So what we see is in general, you have basement rock. This is rift system. In the middle, that's where the fully altered zone exists. Then on the outside, there's like more or less fresh or very fresh igneous rocks. Then in these transition zones, they're synchronized. That's where interesting things happening. So that's actually really cool for us to put all this together. So what does that mean for the geological hydrogen exploration? Now, if you look at the zones that we understand that's been spent, the alterations complete, if you just take top 1 kilometer of igneous rock of these hatched areas, that's where we think geological hydrogen has happened in the past, and the dashed line large areas that have chemical potential. You just take calculation with the iron rich minerals in there, you can estimate this top 1 kilometer zone could have produced 15 gigatons of hydrogen gas in the past. That's enormous. So what does really mean? Put that in the kind of context we can all connect. If you take the 2024 energy consumption in the US, that's shown here in the blue. So that 18 or 15 gigatons of hydrogen gas could power US for 20 years. Now, I have to actually clarify that's what estimates hydrogen that produced in the past. We don't know how much of that is still there. We think most of that is gone because the hydrogen gas will be short-lived. But then how much is remaining, we don't know. That'd be a focus one focus for our research and for the community. And for US, similar regions in other parts of the world that actually, so we're at a stage we can identify the hydrogen systems and identify within that system where to look for. So in the end, what we believe is that we are looking at a civilizational level energy source long into the future. And with that, I'll conclude and want to thank Roxana for the invitation to present and thank all the audience to join us today.
Thank you so much, Dr. Lee. This has been amazing. I actually learned so much here, so I actually appreciate you going into more of the technical detail. And this is so exciting to hear about all the opportunities for the states. I know that for us as the U.S. Hydrogen Alliance, we've been on the hydrogen frontier for half a decade now, before hydrogen really had expanded outside of California very much. And we've been looking at how to create opportunity in the Midwest, and you see there's such a opportunity here, and there's all these beautiful aspects where this exploration is leading to critical minerals. It's creating new opportunities for CO2 sequestration. It's helping with other kinds of like SAF and other kinds of renewable fuels. So there's a lot of interesting things here. We have a couple of questions. Again, please use the Q&A. I have actually some questions that came to me via email if we don't mind addressing that first, and then we're going to go to some of the questions in the chat. What percentage by volume hydrogen in air is needed to be sustained for commercial hydrogen production? And I open this up to all of our speakers.
That's more in Jeff's domain. Guys, go ahead.
Wait, the question is, what is the concentration of hydrogen in air that would constitute
Right, that's the question I had received. What percentage of volume hydrogen in air, in quotation marks, is needed to be sustained for commercial hydrogen production?
Well, yeah, so I guess, I think in air is really not the appropriate qualifier there, but this would be gas accumulation coming out of the subsurface. And, there's not a hard and fast number there, but I've heard anecdotally that you probably need 20% hydrogen to justify the cost of the separation and cleanup that would be needed. But, it depends on what else is there. So if you have helium there, helium can be economic at concentrations even less than 1%. And so if you have a little bit of helium there, that could drive the economics that maybe you could still monetize, 10% hydrogen or something like that. But of course, if you had a bunch of CO2 there, then that could destroy the economics. So it's a really case-by-case situation.
The blessings and curses of hydrogen and its desire to be very reactive.
So let me comment on that 20%. So I echo that number. I think understanding in the community is once you have the concentration of hydrogen produced from underground reach 20%, the current separation technology, such a membrane-based technology, can be actually readily applied without incurring huge amount of cost. So that's a techno-economic analysis that comes into this.
Thank you for bringing that up. That was important. So I have I think to all the doctors, the presence of hydrogen generates anomalies in our data. I've seen some well data, and it also generates anomalies in parameters like GR, resistivity, porosity, and just as we can calculate or identify which zones in these wells contain hydrocarbons, how can we determine which depths of the wells we're studying contain hydrogen? And if I butcher that, it's in the Q&A.
I think that's in Mengli's domain. One of her
Oh.
focuses on the reservoir. So
As we just mentioned, that our strategy for geological hydrogen is source rock centered. So we will explore the source rock first, and we believe it's less likely for geologic hydrogen migrate far away from the source rock. So it should be search the nearby area of the source rock and then find the geophysical signature for the hydrogen accumulation. We have data from UAE about the using seismic data from the seismic signature to identify the potential source rock, the reservoir near the source rock opulite belt. So that's there is no concrete depth. We think the strategy, as I just mentioned, is depends on the source rock distribution and the proper geological setting for hydrogen accumulate.
Thank you. Is there a rough idea or range about the permeability and thickness of seal? Uh, I think of the seal or of steel, like it says SEAL, to ensure hydrogen containment in the reservoir.
Yeah, I can address that. So this notion that hydrogen is so small and diffusive that you just can't trap it and form accumulations of it, it turns out that we're starting to understand that it's not really such a big factor there. That for one thing, if you have a free gas phase that's trapped in against a seal, then diffusivity is not a factor there. It's actually the capillary entry pressure for the gas to get through any pore spaces in that seal. And the capillary entry pressure for hydrogen is actually quite similar to other gases like CO2 and methane. And so I've seen a number of calculations showing that most likely the seals for holding column heights of hydrogen-rich gases are going to be very comparable to what we see for natural gas methane. The column height of a pure hydrogen accumulation is fractionally less than what a pure methane could be trapped under a seal. So typical shales that we see for natural gas reservoirs could also be very effective for holding in hydrogen accumulations as well.
Beautiful, thank you. How feasible is it to combine the green hydrogen production with geothermal energy production? Any examples?
Yeah, I think that's an interesting question and one that I hadn't thought too much about that in the past, but I think it's a great suggestion. And the reason I say that is that these geothermal settings are also places that often generate hydrogen, and many geothermal plants, the steam that they're venting actually contains substantial amounts of hydrogen. I've read that in Iceland now they did some calculations showing that they were probably venting millions of dollars worth of hydrogen every year because they just simply don't trap it. And so I think it's interesting you could actually capture that hydrogen and then also use the water and the steam to run it into an electrolyzer and take the electricity that your geothermal plant is making and using that to split hydrogen. And so I think it's a great notion. I don't know that anyone is really working on that, but I think it's a really good concept.
On
Wow.
that one, let me jump in. I think what Jeff addressed is the extracting naturally occurring hydrogen in the geothermal venting. But the question is about the combining geothermal
Y-
spring
Yeah,
hydrogen. So,
yeah. No, and so, but you could use the electricity from your geothermal plant to run an
right.
electrolyzer and make the
So,
hydrogen, right?
yeah, that's what I want to address is that I think it's technically doable, but I think then that will be an expensive two-way street because the cost of the green hydrogen electrolysis in the US, as last I checked, it's hard to come below $5 per kilo. So using geothermal to generate electricity to do green hydrogen would be an expensive loss proposition. I would actually probably not go with that. So that's just kind of
Yeah.
my opinion.
No, it's a fair point. You'd have to look at the economics of it. But my point is that, if you have economic quantities of hydrogen associated with your geothermal fluid, there might be an advantage if you're building all that hydrogen infrastructure that might actually make the economics more workable, that it might actually be worth it splitting it, putting an electrolyzer there and also generating some green hydrogen with it. It might work out. I don't know.
And I always like to tell our members and those that I work with, none of this is really economical and with in the initial stages. And when we've talked to different policy stakeholders, they've brought up geothermal, and there's even geothermal. We're using some geothermal language as kind of our base language for geologic hydrogen legislatively and from a regulatory standpoint. There might be some incentives for geothermal that we can piggyback on and maybe even add more incentives into the mix, but I want to move forward because there's so many questions. Does software exist that combines the various elements for identifying geologic hydrogen into a program that could help project developers identify sites for projects?
I don't think it's their existing software. So it's all the understanding and knowledge. It's in the stage of developing. Like now we are working on the source rock, but we need more understanding and knowledge from the hydrology. Like our calculation assume we have enough water, but then this part of knowledge we need more to develop it. So it's ongoing understanding and developing that help our refine our model.
I would add, though, that there are commercial software packages that are out there for geologic hydrogen exploration. They're following the petroleum system modeling software approach, and in fact, SLB is one company that they have an existing product for oil and gas exploration, and now they've incorporated geologic hydrogen into their program. And then there are others that built their own software from the bottom up for doing this. So, but as Mengli says, there's still a lot of knowledge gaps. There's a lot of uncertainty in this, and so it's an evolving field that there's a lot more that needs to be done to improve those kind of products.
There is this fun question in here. There's multiple questions, but I'm going to try to get to this really quickly. But Dr. Ellis, I'm thinking about you in this question. Serpentine is prevalent in California. Are there initial exploration efforts taking place in California in addition to the mid-continent rift system?
Yeah, there absolutely are. And as you know, Roxanne, I just got back from Southern California last night. So I was out there with some colleagues from Stanford and some startup company, actually. And so, yeah, there's active exploration going on in California, and the whole west coast of the US actually is quite prospective. And there's a lot of interest out there.
And then how promising are the current projects with stimulated hydrogen? That's broad. I know everybody.
Yeah, I mean, I'm happy. I don't want to. Yeah, Dominic, go ahead. Yeah, well.
Okay, yeah. So there's almost as many activities in the stimulated startup space as the natural hydrogen, and I'm convinced that's a major future direction compared to the natural hydrogen. So the reasons, as actually former ARPA-E program director Doug Wicks has always mentioned that through that we can tap into way more, much more chemical potential versus natural accumulation. And the other aspect is that one emerging direction might be the enhanced hydrogen generation. Basically, you have natural systems. You have to use the method developed in the stimulation realm to enhance natural production to speed up, increase volume. So I would say a simple answer is eventually it will be very promising. Right now, it's in the experimental stage. In fact, one of the things actually, there's a lot of lab work, and then the issue is how to actually transfer the lab result into the field scale. In fact, that's one of the projects actually we're working on. Dr. Zhang's leading is how do you actually use geophysics to monitor what's going on. And for those of you who will be at ARPA-E Summit next week, we'll have stuff showing there. So we'll have to talk about, yeah.
But I
And
will point out that
they
there's, well, can I just jump in
uh,
and just say there already is an active pilot project going on in the country of Oman, and they've had some amazingly successful results already. Surprisingly, they did an injection of just pure water and generated much more hydrogen than they anticipated just on that simple test. And so that was very encouraging. And as I understand it, there's also another pilot project that's planned to start later this year in Quebec in Canada. So we are moving already very quickly out of the lab and out to the pilot scale. So definitely stay tuned. I totally agree with Yago that I think there could be way more potential in the stimulated side than in the accumulations. That's yet to be seen.
Yeah, they are near 20 teams supported by ARPA-E will present their tech show in the coming week at ARPA-E Energy Summit. So that there are more information there.
Yeah, all on stimulated hydrogen. Yeah.
Mm.
So we're at the top of the next hour, and we haven't even come close to answering all the questions. There are some folks that want to become your students, so we'll send you more of that information. What we're gonna do is share these extra questions with our distinguished speakers and see if they can answer them offline, and we'll send that in the email recap by tomorrow. But I want to thank our speakers for contributing their expertise on this topic. Obviously, it's a hot topic, and I want to thank you all for your attention and your participation. And I hope you have a fantastic week, and you'll hear from us more. Okay, thank you, everybody.
Thanks, everyone.
Thank you.
Yeah, thank you, Roxana.
Thank you.